Hi, so I'm going to be sticking with the same theme, with looking at evolutionary relationships of jawless fish, but I'm going to be focusing on the Heterostracans. So most of us know that today vertebrates are a really important component to ecosystems and life on this planet. But the majority of vertebrate taxa today fall within the jawed vertebrates or the crown gnathostomes. And the only other living group of vertebrates are the cartilaginous hagfish and lamprey. And these don't have a mineralized component to their skeleton and have a really poor fossil record and don't give us much indication about how the vertebrate skeleton evolved. Lucky for us, we have the fossil record, and positioned between these two living groups are an extinct paraphyletic assemblage of jawless vertebrates. These Paleozoic fishes see the first appearance of many vertebrate features, such as the first appearance of bone, paired appendages, paired sensory organs, and endo and dermal skeletons. However, the evolutionary relationships, as Joe shows, of the jawed vertebrate stem are quite contentious. Two recent phylogenies, both concentrating on anaspids, have placed the anaspids as the deepest branching skeletonizing vertebrates, whereas the phylogeny of Keating and Donoghue placed the pterospidomorphs as deepest branching skeletonizing vertebrates. And it's the pterospidomorphs that I'm going to focus on today. So within the pterospidomorphs, you have the Heterostracans and the Arandaspids and Astraspids. So the Ordovician pterospidomorphs are a handful of articulated vertebrate skeletons from the Ordovician. These include Arandaspis and Saccomambasis, which were found in the southern continent of Gondwana, and these forms have these large singular plated dorsal and ventral plates with an anterior mouth. Whereas another form, Astraspis, has a dermal head shield composed of small tessellate platelets which cover the head of the animal. And it's not really well understood which of these groups is the sister lineage to Heterostracans. So Heterostracans are taxonomically the largest group of stem-jawed vertebrates, with over 130 genera and 300 species. Synaphomorphia of the group is having a single pair of branchial openings, which is sometimes but not always covered by a branchial plate. They have a bony armour dermal skeleton covering their head shields, and this is composed of a type of acellular bone called aspidin. This is sometimes but always covered in this quite often beautiful ornament, which is composed of enamel and dentine. There are many different lineages within the Heterostracans, but only two, the Saspids and Pterospidiforms, have actually been included within any phylogenetic analysis. So the group as a whole has been lacking a phylogenetic hypothesis of their evolutionary relationships. And as Joe said, this might have great ramifications for the resolution of the jawed vertebrate stem. So the aim of my work has been to create the first phylogeny to include all taxonomic described genera. This will allow me to identify the plesiomorphic condition within Heterostracans and vertebrates as a whole. Then it will allow me to identify the evolutionary relationships within the Heterostracans and their position on the jawed vertebrate stem. So as in many phylogenies, a big problem I faced is that of identifying homologous features. So one of the biggest distinctions I made in my phylogeny was between multiplated forms and non-multiplated forms. So all these taxa here have a head shield composed of many different plates with varying degrees of arrangement of these. Whereas other forms have a head shield composed of singular dorsal and ventral plates. As with many groups, there are a lot of problematic Heterostracans which have not been included in any phylogenetic analysis. This includes forms which have a really poor fossil record, are fragmented, and are articulate, or forms such as Cardipaltus, which have such an unusual anatomy, it's not really comparable to any other groups. And another branch of the Problematica are the tessellate Heterostracans. These have a head shield composed of singular dorsal bony elements, which means they're hardly ever found articulated. This includes Tesseraspis, which is housed here at the Lapworth Museum, which has separate bony elements, whereas Lepidaspis has these separate elements that fuse on maturity. And as I said, hardly any of the groups have actually undergone any phylogenetic analysis, with most of these previous analyses focusing on the Pterospidiforms and the Saspididae. These are some hypotheses of the relationships going back for many different workers, but it's only Tarlow and Janvier that have actually included the problematic and tessellate in their hypotheses. And both of them have placed them in a kind of basal, envisaged them as a plesiomorphic condition of Heterostracans. But no one has yet performed the whole group analysis. So building upon my previous two papers, which include the Pterospidiforms and Psilocybidae, I have included all the different taxonomic groups, which resulted in 145 in-group taxa. And I've also used 21 out-group taxa, which include vertebrates and non-vertebrates, and this builds upon a long history of work by Janvier, Smith, Donoghue, Guest, Gabbett, Sansom. So I've got quite a good sample, I hope, of non-heterostracan vertebrates. I included, totaling in my analysis, I have 243 characters, 25 of which are continuous and 25 discretized, and this is so I could include quantitative data within my analyses. I performed parsimony analysis and TNT, and I also assessed the difference to my different coding methods using stratigraphic congruence. So moving on to the results, as identified by a previous paper, transforming the quantitative data into discrete characters seemed the most appropriate method for my data and gives the most stratigraphic congruent results. So I'll be focusing on that for the majority of the talk. So my results indicate that I have a monophyletic heterostraci, but this is in a polytomy with the Ordovician forms as the deepest branching skeletonizing vertebrates. So I don't recover a monophyletic pterospidomorph. And as you can see, I don't really have much resolution towards the base of my tree. I've just kind of color-coded the previous taxonomic interpretations of these, and many of the forms in this large polytomy seem to be the large plated forms on the tessellate and problematic taxa, whereas further up the tree with much better resolution are the multiplated forms. When we were looking through our tree files, we kept coming across two consistent patterns within the most parsimonious trees. And so we decided to explore this further. So we decided to use the tree set viz package in Mesquite, which uses the Robinson's fold tree differences, which assesses similarity between tree topologies to see if we could recover these two patterns. So we sampled 10,000 trees, and using multidimensional scaling, as you can see here, we can visualize these differences of tree topologies in this space here. And you can see there's quite two discrete clusters or islands of trees within our data. So the strict consensus of these two trees you can see here. There's a kind of a 50-50 split between the data. And the first recovers the classic view of heterostracan evolution relationships, which has the tessellate and problematic taxa as the sister group to all of the heterostracans. Whereas in the other cluster, so these are both, all these results are equally most parsimonious trees. In the other cluster, we have the Cyaspid, or the large plated forms, in this position as the sister group to all other vertebrates, heterostracans, sorry. And this has great implications about the plesiomorphic conditions of heterostracans. So were they tessellate, or were they multiplated, and perhaps vertebrates as a whole. I did run the analysis which left the quantitative data raw, and this recovered the large plated forms in this kind of basal sister group to all of the heterostracan position. But as showed by my previous work, having the raw continuous data doesn't give us that good fit to their fossil record. So I used stratigraphic congruence, which assesses the stratigraphic distribution of the fossils in time and their tree topology, to see if I could get kind of an idea of which tree topologies kind of fit better with their stratigraphic record. And in all instances, the discretized analyses seem to perform better than the continuous, and it seems that cluster 2, which is the large plated forms, seems to give us the most stratically congruent trees. So perhaps these trees are giving us kind of a more realized view of heterostracan evolution relationships. So just to summarize, I recovered a monophyletic heterostraci in all instances, and heterostracans, along with the Ordovician pterospidomorphs, were found to be the deepest branching skeletonizing vertebrates. But I didn't recover monophyletic pterospidomorphs as a classic hypothesis of these relationships state. There are conflicting models in the plesiomorphic condition for heterostracans, and stratigraphic congruence points towards a tenaspid, or the large plated forms being the kind of truer tree maybe. So this is the first phylogenetic analysis to include all the heterostracans with all the problematica. And it's hoped that with this analysis, we can then look at other macroevolutionary patterns in these stem-jawed vertebrates, such as dispersal trajectories and other things. So I'd just like to move on to say thank you to all museum staff for housing me and allowing me to visit their collections, Dr. Joe Keating for the cartoons in the earlier in the introduction and discussion of vertebrate characters, the Manchester Paleobiology Group, SCPCA for a travel grant, and thank you for listening.